Okay guys, we're on section 2.5, section E, starting with the vocab. Average rate of change, basically that means the same thing as slope, the delta y over delta x, or change in y's over change of x. So if you're looking at the average rate of change on this function here, we're going to look at from the interval from x equals -3 to x equals -2. So basically you're going to plug in the value of f of -2, that's the y value of this function at -2, subtract the y value of the function at -3, and divide by x minus x, which is -2 minus a -3. So you can either plug in the function -2 algebraically and solve, or you can plug this function into your graphing calculator and trace it to the point of -2. Find the value of the function at -2 is 4.5. Value of the function at -3 is 0. -2 minus -3 is like adding, which is 1. So that slope is from an average rate of change of 4.5. You can do the same thing from -2 to -1, so the function at -1 minus the function at -2, all of the difference of -1 minus -2. With those values you plug into your calculator, you get 4 and 4.5, the difference of that over 1. That difference is now -0.5. So the average rate of change from -2 to -1 is now going down by 0.5. Do the same thing again from 0 minus the value of the function at -1, all over 0 minus -1. This is 1.5 at 0, 4 at -1, all over 1, which the slope now is at -2.5. If we sketch these values, you can see what's happening at these points. If you look at the function, these x-intercepts are happening at +1 for a 0, and then at -3 for a 0. You can look at this on your graphing calculator screen, or you can punch in some other values, like if you plug in 0, you get the value of in between 1 and 2, or 1.5, and then up here at -1, you get another value of 4. You can continue to plot some points in there and see some values, and then you realize this is a cubic function. It's going to start low, bounce through these points, come around and hit the x-axis at 1 and bounce off, because that was an even power on that one. Okay, so if you look at each of these values, what this means is the f of x is increasing quickly from -3 to -2. So if you're looking from -3 to -2, if you actually find the slope between these 2 points, that line is increasing rapidly. That has a positive 4.5 slope. But then if you look from -2 to -1 and you connect those 2 points, that line is now decreasing, so f of x is decreasing from x is equal to -2 to -1. That slope was -0.5. And then if you look further, if you connect the points from -1 to 0 on the x points, that slope, that line is decreasing as well. So from -1 to 0, it's decreasing, but this one's decreasing even faster because that slope is -2.5 compared to the -0.5. So you're basically finding points of secant lines through there to see what the slope is. On the next example, we have a stone. It's thrown vertically at initial speed of 50 feet per second. The height of the stone can be modeled by this equation where you've got gravity, velocity, and initial height. The stone's height at 0.5 seconds, you literally are plugging in 0.5 for the t and solving. That value would be 25. If you pause, you can do these on your own and come back and turn the tape on and see what you're getting. If you plug in 1, you get 38. If you plug in 1.5, you get 43. So this time if you're doing average rate of change from 0.5 to 1, you're finding the y values of 38 and 25. Subtracting those, and the x values was from 1 second, subtract to the 0.5 seconds. And you get that 13 divided by 0.5, you get an answer of 26 feet per second is the average rate of change from half a second to 1 second. If you do this again between 1 second and 1.5 seconds, the heights are 43 and 38, and then the x values are 1.5 seconds to 1 second. That's 5 divided by 0.5, or 10 feet per second. So it's going slower at this point because it's getting up toward its maximum. So as it's, both of them represent going up. However, from 1 to 1.5, it's nearing the max. That's why it's got a smaller average rate of change. It's going 10 feet per second because it's slowing down right before it starts its decline. Next part here, we're going to go through some vocab. The difference quotient represents the average rate of change between the x and the x plus h values. There are two values that are very close together. Equivalently, the difference quotient represents the slope of the secant line for this interval. So the difference quotient, it does look a lot like the slope formula where you have you're plugging in your value for x plus h, the y value, and then plugging in x and getting the y value of that coordinate over h, which basically is the interval between x and x plus h, how much distance spans those 2 points on the x direction. So if we're looking at this next one, we're going to compute the quotient difference by plugging into this formula. I'll put that formula back here. So we're going to be taking f and plugging in x plus h into the function, and then we just subtract the original function, and then we divide that by h. So if we look at the values of this function, we're going to plug in x plus h into our function. That means square it, subtract 3 times it, and add 4. And then we're going to subtract the entire original function, x squared minus 3x plus 4. And we're going to divide all that by h. In the numerator, we have to FOIL the first one. That's x squared plus 2xh plus h squared. Second part, you're going to distribute the negative 3x minus 3h. And the last set, this negative goes to everything in our original function and changes all the signs. If you start simplifying this, x squared minus x squared is going to disappear. And then you have negative 3x and positive 3x is going to disappear. Plus 4 and negative 4 is going to disappear. And in the numerator, you're left with 2xh, h squared, and minus 3h. You notice that there is a common term to the numerator. If you pull the h out, you're left with 2x, 1h, and a 3 all over h. If you cancel the h's off, your difference quotient is just 2x plus h minus 3. So we're finding the average rate of change between 0.9 and 1, and then you can go from all the way up to the point of negative 3.1 to 3.2. So we're going to find the average rate of change between 2 intervals. So the first interval from 0.9 to 1, x is equal to 0.9, because that's the first value in our coordinate. H is the difference between those. So h, we had a distance of 0.1 to separate those. If we actually plug this into the formula we just found the difference quotient to be, that would be 2 times 0.9 for the x value, plus h value is 0.1, minus 3. That's equal to negative 1.1. If we do this again for the next interval, 3.1 to 3.2, the x value is 3.1. The h value, again, to go from 3.1 to 3.2 is 0.1 units. If we plug that into our difference quotient equation, 2 times the x value of 3.1 plus the h value of 0.1, subtract 3 is equal to 3.3. So if you look at this graphically, if we took x squared minus 3x plus 4, you're going to have basically a quadratic equation. Looks like a parabola. It's opening up. And if you literally graph those points from 0.9 to 1, and you connected, plotting that point from 0.9 to 1, that slope of the line is decreasing at a slope of negative 1.1. If you look at the difference between the points of 3.1 and 3.2, if you plot 3.1 and 3.2, they're very close together again, and that is much steeper. If you connect those points, that slope is 3.3. So from 0.9, this comment here, from 0.9 to 1, it is decreasing, and it's going down at a slope of 1.1. And then from 3.1 to 3.2, it's increasing, and it's much steeper, or it's going faster going up on that part. And you can do page 156, number 77 is another example if you want, or wait until class and do some of your homework problems. And that's it.